Hello everyone, I'm Beta, your host for this talk. On behalf of TMLS team, I want to welcome you to the MLOps 2020 conference. Feel free to ask your questions during the talk in the chat section, and I will ask your question during Q&A at the end of the talk. This year, we are honored to have great speakers with us. One of them is John, a modern polymath. John possesses a unique and diverse set of skills, knowledge, and experience, having earned advanced degrees in mechanical engineering, kinesiology, and data science. His expertise focuses on machine learning solutions to novel and ambiguous problems. He has a proven history of taking a problem from idea to production by using a logical but creative data-driven approach. As a senior applied data scientist at Amazon, John led the Alexa Skills Store science team. He worked closely with engineering to build systems that enabled Alexa customers to engage with third-party applications. He built machine learning models to arbitrate between skills, entity resolution, search, and personalization. Currently, John is a principal data scientist at Oracle. He works on the data science service as part of the Oracle Cloud Infrastructure team, leveraging his extensive hands-on experience building machine learning models. He's now defining the tooling to improve the data science workflow. John fosters the growth of scientists by starting the Amazon Machine Learning University, the Alexa-wide Data Science Excellence Program. He frequently gives talks at universities and conferences. He also coordinates the largest R meetup group in Southern California. So, John, if you're ready, we can start.
Hello, welcome everyone. Thank you very much for coming to my talk. So I got interested in sort of the tooling around data science to sort of solve my own niche problems. I trained as a classic scientist. I've done way more stuff in Excel than I care to mention. And I found that, it's very repetitive. So I started like writing code to do a lot of the clicking for me. And I did a lot of consulting work and it was fine. It was a lot of one-off stuff. And then, so I had a career. I used to be a professor. And when I left that and went into industry, I was very excited about learning new tools on how to do my work better. And so I started working at a medium-sized company and found out that the tooling that they had around software development was excellent, but the tooling that they had around data science was still very primitive. So I started to develop some techniques using the basic principles of literate statistical programming, which come out of literate programming, which is a common foundation in software development. And then I went to a small startup and used those same things. And then when I went to Amazon, I was expecting all this great tooling that they would have because they have thousands of scientists working on scale. And they had some, but they really sort of lacked sort of the end-to-end flow that you would need for robust, repeatable research. So I implemented a lot of what I'm going to show you there. And now I'm working on focus is basically getting a product developed that will allow us to use literate statistical programming. So we just released our service in February. It's very, very new. So I'm working on implementing some of these ideas into the products to build basic data science tools that everyone can use, from a single person to a small startup to large-scale corporations. So let me share my slide deck. So some of the things that we're going to talk about, we're going to talk about the problems around science and replication. What is literate programming? What is literate statistical programming? How does it vary? Some of the problems with the status quo tools that we have, and then where we should be going to be building out solutions to these problems. And the unfortunate thing is I don't have something that I could show you today and say, hey, this is the greatest tool that and it solves all these problems. We're still very much in the early days of literate statistical programming. If you do a Google search on LSP, you'll find very, very little information. So it's something that I'm pushing that becomes sort of part of the natural thought process for scientists and part of a standardized tool set to handle the varied different problems that data scientists face and the different ways that they work. So replication is the core concept of science. Um, Replication is actually really hard to do, and we're doing less of it now than what we used to. So from an academic point of view, it's really hard to fund studies that are replications. These funding agencies basically come back and say, hey, we've done this already. Publications are hard to publish when you are just replicating somebody else's results. They tend to go into lower tier journals, or they're technically just not possible. It was a one-off event. For example, there was a great study that was done, unfortunately, out of 9/11, where all the planes stopped flying, and they were able to show the environmental impact of the contrails that planes were creating on the temperature. I mean, that's something we can do now with COVID-19, but it's nothing that's generally planned for. Um, and in terms of industry, these problems become far worse. There's very, very little replication within industry. It tends to be you do the study, you get the result, and then you move forward. And there's less drive for the truth. So we need to be able to build replication into our work so that we can handle it from an auditing point of view, so that you're not going to do the same study twice. What we're going to do is we're going to go back and audit what we did. So some of the challenges that we have around this is there's not a lot of training that people coming with PhDs and are data scientists. It's just not the way that they worked. And there's also difficulties around tooling. There's very little tooling. It's a little piecemeal. There's gaps. And so I'm working now to try to fill some of those gaps. So the focus of this talk, since it's an ML Ops conference, is going to be focusing on the tooling. I could give you talks on each one of the points above, but let's focus on the tooling and where we are today and where we're going. So the tooling problem. You'll often see diagrams that show sort of the scientific method, and what I have here is design thinking for data science. It's a process, and it looks fairly linear. You start off by empathizing with the customer, you then define the problem, you ideate on the problem, you build a prototype, and you test. But that's not actually the way we work. It makes a nice diagram, but you'll empathize, you'll define, you'll iterate, and then you'll realize like, oh, you didn't like really define the problem very well, and you go back and you redefine, and then you'll move on to ideate again and prototype, and then go back and like, oh, well, we didn't really fully understand the customer problem, so then you go back to empathize. So it's not this linear process that you're going to build out a streamlined pipeline. You need to have tooling that is going to allow you to replicate your work, branch, merge, come back together, split off again, circle back and forth. And we don't have today the tooling around that reproducibility, and we don't have the processes in place to do this. And this is what literate statistical programming is going to do for us. If you follow this techniques, it will allow you to have all that branching and merging and circling back and working on a problem and still track everything. So what is literate statistical programming? So it's a way of working where you have one document, and by one document, it can be multiple documents that link into each other. But one document, it's a stream of information where you have human readable text and machine readable code sitting side by side together. So to give you an example, you would have your analysis where you'd make a histogram. So you would have the code for that histogram sitting right there, and then your interpretation of the histogram, the end results that you're seeing, that would sit right there with it too. So as you change your data, the histogram would change, and then you just changed your text right in place. They're living together, they're not separate. It's not like you build your histogram in one tool and then you copy and paste it into Word. And then when the data changes, you don't update the Word document. You want them living and breathing together in one place. So this stream can then be divided into two operations. So you have a weave operation, which the end result is a human readable document. And this is what you're going to pass off to your managers, the decision makers. This is going to give them the information that they need in order to make a decision based on the data. And then you're going to have Tangle document, which is the machine readable code. This is the stuff that's going to actually do the analysis for you. And you want them living side by side so that when you update one, you can update the other. But you don't want to be handing over to your manager, hundreds of or thousands of lines of code. They're not interested in that. It dilutes the message that you're trying to pass off to them. So literate statistical programming is a way of writing your code and writing your analysis so they live together. You get two documents on the outside. One is weaved, which is the human readable. The other one is tangled, which is the machine readable document. And by machine readable document, it may be like a machine learning model or something like that. So literate programming is commonly used by software developers. It was developed by Don Knuth at Stanford in 1984. He proposed this concept and built an application called Web. He then updated the concept in 1990. And the idea is basically that you have this machine readable documentation and human readable documentation living together, and you tangle and weave the two of them together. So what does this look like? So I'm going to give you examples in R and examples in Python. So those are the two most common languages used in data science. So in R, we do literate programming. We use something called R Oxygen 2, where what we have on the top here is the documentation that goes with this very simple function that I have. So you give the function a title, mean value, you give the function a description, determine the mean value of a vector, and then you define the parameters. So the parameter x is a numeric vector of values, and then you can give some examples. And when you would take this, you would run it through another process, you would weave it, and you would get the documentation that would show up in your IDE. Right beside that is the actual code associated with the documentation. So if I decided to change mean, I can change my documentation right there. It's up to the developer to change the documentation. They live side by side, they breathe together. If we were to do this in Python, you define a function mean, and then you use hair docs. And within the hair docs, you write whatever you want. So I basically have the same thing. I have a definition, I have a description, I define my parameters, and I define what the return value is. And then right below that, I would have my, in this case, very simple Python function. I'm going to return x divided by the length of x. And that should actually be sum. There's a typo there. Sum x divided by the length of x. So what's the differences between literate statistical programming and literate programming? So I just showed you literate programming. In literate programming, the code is primary. It's at the end of the day, software developers write code as the end product. The documentation is very important, but it is optional, right? Their code will still run without the documentation. The documentation makes it much easier for their future selves when they go back to edit it, for sharing with our developers, exposing APIs, that type of stuff. But it is optional. The code is primary. In literate statistical programming, it's the opposite. It's the communication of the analysis is primary. My manager is not really interested in the code that I wrote to do the analysis. They're interested in the analysis so that they can make decisions on how to move forward. So that is primary. The code is secondary to it. I want the code to live and breathe beside my analysis so that I can go back and audit it, fix bugs, rerun it as the data changes, redo my analysis so they're not disconnected from each other, but the primary output is the communication. So what are the types of products that I'm going to be handing over as a data scientist? Well, it falls into a couple of different categories. So you can have a standard written report, and I call this a consultation style report, where this is you're going to write a document, you're going to hand it over to a customer, and then they're going to make some type of decision based off of that. Or you can also have institutional memory style documents. So they're not going to be read by probably anybody other than you. It's to help you understand the nature of your data, maybe help define what a problem is going to be before you're going to be handing it over to people that are actually going to be making the decisions on how to move forward. So you're documenting all your work in progress. And what happens a lot of the times now is the institutional memory style documents just doesn't get written. It sits in somebody's head. And when they change organizations or change roles within the company, all that goes away. And with the literate statistical programming, that all stays. The other big output that we have are models. So the models would be going into production generally, or some form of testing would be done on them. And there may not necessarily be a whole lot of written documentation that goes with it, other than explaining the assumptions that went into the model. And these need to live together. You can't have a model in production and somebody says, what does this do? And we're like, I don't know, we got it from Sally. There has to be some sort of documentation that ties that model to what the assumptions were, what the model is actually doing. So they shouldn't be decoupled from each other. The model and the analysis live together, and you may not have an important document that you would want to share, but there is documentation. The important takeaway from this is that what we don't save is the output. What we save is the pipeline. So we're going to get reproducibility for free by not storing what the output was. What we store is how to get the output. So as I was mentioning before, we're always circling around different stages of the process, and we're going to have not one report, but there's going to be hundreds or thousands of in work in progress reports that are being developed. So what we save is the pipeline in order to get those reports. Now you can like generate a consultant report and store it somewheres. That's fine. But my point is that you're not saving individual versions of the output. You're saving the process to build the output, because the output is always going to be changing. So what is the state of the art today? So I'm going to go over the two primary tools that are used in industry. So within the R programming language, most data scientists use RStudio, and they use a tool Knitr. It should be pointed out that Knitr is not actually specific to R. It's very unfortunate that it's called knitr. Knitr actually supports, I think it's around 30 different languages, Python being one of them. So what I'm going to show you through the Knitr, I'm going to use R as examples, but if you're a Python programmer, you could just as easily go and use Python and get all the advantages of that. But what you're going to generate is an R Markdown document, which again is unfortunately named. It's really a Markdown document where a language sits on top of it, a programming language sits on top of it. And we can generate LaTeX documents, so you have all the full power of LaTeX, and you can also get HTML documents out of it. The other very common tool used mostly in Python, but also supports R and Scala and other languages, is Jupyter Lab. And here you have individual cells that you write code in, and you have Markdown that sits side by side together. And I'm going to go over sort of the advantages and disadvantages of each one of these. So literate statistical programming in Knitr. So your code is done in two different ways. You don't have chunks per se or blocks. You basically have a free-form document. And if you want to execute a chunk of code, you would go tick, tick, tick. You specify the language. In this case, I'm saying R. I'm telling it don't output the code into the document, and I want you to run this document, run this code. So in this case, I'm taking the numbers 1 through 10, I'm doing a t-test, and I'm storing that into result, and I'm storing 0.05 into beta. So this is code that's going to run in the document, and then below that I have Markdown. So Markdown, if you don't know, is a markup language that you can learn in 15 minutes. It's super simple, and it has just a few basic operations, but allows you to have nicely formatted documents without a whole lot of complexity. It's kind of like a lazy man's version of HTML. So sitting right in the same document, I have the code up above, and then I have some text. So I have the test shows that the p-value was, and then I have inline code. So I have here just a single tick. I then specify my language R. If I want to use Python, I would just put Python there. And then I say format the output from the results variable with a p-value. And so in the text below at the bottom of the slide, I have the test shows that the p-value was 0.0 blah, 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 27. What I have now is a document that when my data changes and I rerun that pipeline again, I will get a new p-value printed there. I don't have to go back and remember to change that. It's a very common problem with people using Word and stuff like that, is that you have a disconnect between the code and the analysis, and your Word document always has mistakes in it because there's certain things you forgot to update because you're iterating over so quickly. So here the output is a nice LaTeX document. You don't need to know LaTeX, by the way. And you have your values produced right in it. So this is an example of a literate statistical program written in Knitr. At the very top, I have a title, an author, a date, and the document type that I'm going to output. So it's going to be a PDF. So this was a paper that I published with my wife. I have some R code here where I set up my libraries. Oops. And then I have some headings. I have some written text, and then more written text, and then I have my analysis code. I also have some LaTeX functionality written into this. So my code and my text live side by side together. And this is what the output would look like. So this is a PDF that was generated from that report. You have the full functionality of LaTeX. You don't have to use LaTeX, but you have the full functionality. So here I was able to embed in a graphic. This was not a copy and paste graphic. This was an image that was pulled off the disk and inserted into the document. I can do fancy LaTeX things like put page numbers and put my name on the bottom of each page. I can do even more fancy things like here I have citations. So the citations is completely handled by LaTeX. I just write my text and do the citation, and it will generate the citations for me. It will also build my bibliography for me as well. So as my analysis changes, I just change the document, and then it will regenerate and build out a properly cited document with a full bibliography. I can also do other things like write equations. So here I have two equations. I have, a nice LaTeX written out equation, but I can also have inline equations, and I can also have a figure here. And this figure is not an image stored on a disk. This is the output from the R code itself that generates the plot and then gets stuck into the document and gets laid out into the document. And you can see that there's equation numbers and figure numbers that are embedded in it. In terms of using Jupyter Lab, it has a slightly different paradigm. So it focuses on having two chunks. You have a code chunk, which I have up above, where I'm calculating the p-value, and then I have the output, and I'm just going to print the number. It's not laid out as well. So this is an example of what it looks like. I have here a code chunk in my document. If I want to have something nice that says scikit accuracy on a test data is, and then print a number, I actually have to write some code and have that the code output print the text. So if you noticed back here, I didn't have any code in my document. My manager doesn't want to read my code. In Jupyter Labs, I have to have the code sitting with my document, but I get nice things like pretty graphics for free, but at the same time, I have sort of ugly computer code that's being printed out. So what are the key issues that we're facing? We have problems around fragmentation, nonlinear workflow, rework of analysis. We have collaboration changes, and we also have to do pipelining activities that aren't typically done by data scientists. So let's take a look at each one of these and how we can solve them. So the fragmentation problem, the code and the analysis and the model are often fragmented. They're not tied together. We need to save the code, the analysis, and the model as a state in one thing that's one object or one collection of things that I can tie together. So when I'm looking at a model, I can go back to the exact code and um, data that was used to produce that model. So how can I do that? So we can use version control of our Knitter and Jupyter Lab notebooks. So everything is going to be stored into text files under version control. We have the central trunk being the main product. This is where we're going to be releasing different versions of our work product, whether that work product is a model or a document or both. Then we use branching within version control, so within Git, to test out ideas and test out different hypotheses. Most of what I do as a data scientist, I prove myself wrong, right? I do some work, I have some hypothesis, I test it, it works out or it doesn't work out. So I'm going to do those all in side branches. And when I find something that's interesting, I move that into the main branch. In terms of the main artifact that we're going to have is every project is going to be a package in R or a module in Python, and each one of these is going to go into its own Git repo. So each analysis is a repo onto itself. If the data is small, I would also suggest that you put the data under version control so that you know what data you used. If the data is large, don't. But you can put the commands to generate it, like the SQL commands or something like that. But one of the problems with the tooling that we have there is that the model is decoupled from the production. Um, so we build a model, we release that model to engineering, engineering puts it into production, and then the question becomes, what was used to build that model? Like, show me the code for that model. Well, the code has now changed, right? We're iterating very rapidly. So Oracle, who I work for, we have solved this problem by basically having a concept of a project. So within our tooling, you have a project. You can have multiple Git repos within that, and then you have model artifacts. So now the model artifact belongs to a project, your code belongs to a project, the Git repo belongs to a project, your data belongs to the project. It's all contained together in one system. We have nonlinear workflow. So science is highly nonlinear. It's my joke is that it's not really a funny joke, but my joke is that once you know how to do something, it's no longer science, it's tech work. And so you're constantly trying out new things and failing in science all the time, and you need to be able to iterate very quickly. So you try out an idea, you keep it or you discard it. And we need tooling around that handles that divergent process. So when we do our report writing, the analysis is done, and we're going to do that. So as we're doing this nonlinear work, the analysis is always changing as we're doing the work. So you don't sit down, do your analysis, and write the report. It's as you're doing the analysis, you write the report. And we're going to use advanced typesetting techniques like LaTeX or Markdown, and we're going to weave and tangle that document together. And at the end of the day, you're going to have a very long document, and you have to have the ability to suppress sections that aren't particularly interesting, that you don't want to communicate up, or portions of the model that you don't want to build out. And often I'll build like thousands of models, and then I select one, right? So I want to get rid of the thousands and just keep the one that I'm interested in. So we have here the concept of you have a trunk where you accept the work, and then you work in branches, and then you merge that work back into the trunk. But the key point here is that you're going to keep a lot of the work outside of the trunk. The stuff that you're handling that's non-linear, right? Once you figure out what works, you merge it back into the linear trunk. So the problem here still is that the models are decoupled from the code in production. So the solution is that you create immutable model artifacts, and then you store metadata that links those model artifacts to the code. So what we've gone and done is you produce a model artifact which has your Python or your R code in it, and part of that, there's a metadata that then points to the Git repo and the hash commit that was used to build that model, so that when we push that model into production, we can't ever change that model. If we ever needed to change the model, we create a new one, and then we can always go back and say, okay, this model in production, it was made by this Git repo and it was made under this commit, and we can go back and we can do an audit there, figuring out like why the model's working or not working. So production models are linked to the model artifacts by tracking that this model went into production through commit changes. So change management systems that are commonly used in software development. Anytime you push something into production, there is basically release notes that go with it. Rework of analysis. So the analysis is never done once. We're going to sit down and repeat the analysis over and over again. You're going to start with an idea. You're going to test some hypothesis. As you learn more about the data, more about the problem is the scope of the project is going to grow as your understanding grows. But we want to work within one environment. We want to be able to do everything we need to do within a standardized set of tools, that we can have this appearance of this linear process, but being very nonlinear. We want to be able to update the analysis as the data changes, and we want to be able to rerun the analysis. So as you develop a new idea, a new hypothesis, you just rerun the analysis. You don't have to go back and rework stuff. And as your data changes, what you're going to find is you made some assumption, like you said, hey, this variable was normally distributed. And then you get a new set of data. And now that assumption is no longer true, and maybe it's right skewed. And your model now is going to fail. So your code is acting as a live regression test. You made this assumption, this variable was normally distributed. When you do the analysis, you're checking for that in your code, and your model is now failing, and you're like, oh, because it's no longer normally distributed, it's right skewed. So this code acts as your live regression tests on the assumptions that you're making in the modeling process. We're not talking about the tests for your code's correctness. We're talking about the tests for the assumptions that you're making in the model. Are built into the code, and it acts as a live regression test. Every time you run your pipeline, you get a test that says, hey, this is failing because of some shift that's happened in your data. So the tooling around this, we're going to use version control, but we're going to use flexible standards. And the standards are not going to be standards that are necessarily documented in terms of like going to a website and say, this is the standards on how we do the analysis. That's far too rigid. What you do is you code the standards into your model. And all data is going to live in files. So you're not going to be clicking on things or manually changing variables. Let's say you were to standardize a variable by centering it so the mean is 0 and having a standard deviation of 1. You write code to do that dynamically based on the data that's there, as opposed to going like, mean was 5, and I'm going to subtract away 5, so now my mean is 0. You write code that computes the mean, and then code that removes that mean. We want to use a cloud-based environment to integrate all our tooling. What's sitting on my laptop, only I can access, or only I should be able to access. We want to have an environment where we can share and integrate everything together. And we want to create immutable artifacts so that as we do rework, we are saving previous work so that we can always go back to it. You may have a hypothesis that you go and you test, and then you come back and you're like, oh, what was that value before? All that should be there. We want to be able to collaborate. So data lives in different locations. We want to be able to audit changes. We want mechanisms to prevent data losses. The cloud provides all of this for us basically for free. We want to know what is the most recent version. We want to be able to share our work and manage parallel workflows. So the tooling around that is standardization. So use a Git branching policy like Git flow. You have central data repositories as opposed to data sitting on people's individual laptops. Even if it's a small amount of data, it should sit in a central repository. Then we have cloud-based solutions because they give us access control, shareability, high availability, automatic backup for free. We want to pipeline our activities, but you don't want to spend all your time pipelining. You want to pipeline what is reasonable, so you may have some manual process as you work through developing your analysis, because you don't know what your analysis is going to look like at the beginning. So premature optimization is wasteful, but once you find yourself repeating something a couple of times, if you can just go back and pipeline that and stream it. You also want to do caching. A lot of data science is computationally very expensive. It can take long periods of time to run. So what I do is I would cache a model result. And when I rebuild the model, if the stuff before it hasn't changed, then it just picks up the old model and uses it. If it has changed, then the model is out of date. So I go back and have it rebuild the new model. You want to strive for no copying and pasting. This is just extremely error prone. If you find yourself copying and pasting something, that is a good thing that you should go and pipeline. All data is to sit in machine readable files, but not in the file names, the paths, or even the notebooks, right? You want to encode file names so that you understand what is in the file, but you shouldn't be parsing file names or parsing file paths. This data should sit in the actual data file itself. You also want to pipeline your data cleaning and validation. This is often done once by data scientists. It's a very laborious process, but that actually should be all automated, so that as you get new data coming in, that it gets the full stream of cleaning and validation on it. And this is part of having your code be live tests. As the data comes in, if it's failing the data validation, then you need to go and fix your models that are associated with that. So the tooling around this, with every change in the model or the analysis, we want to rerun the pipeline from beginning to end, and it's all right to speed things up with caching. We want to strive for a one-step process, even though you'll probably rarely ever get there, but you want to be working towards click a button, get an analysis, you get a model in production, and you get a paper report. You use config files to manage your pipeline, not having somebody manually go and click and adjust things. You want to write data unit tests. So unit tests in software development are tests on like an individual function. You want to write these same types of tests on your data. I'm assuming that this data is normally distributed, it's between this range, it has a variance within this range. You want to actually write a test that checks all of that, so that when it's running through your pipeline, if your data changes, you become aware of that. And you want to dynamically create reports that don't have hard-coded values, tables, and figures. As the data shifts, you just want those automatically created for you. So in summary, Literate Statistical Program helps us with reproducibility. It addresses the fragmentation problem where we're working on different components that are disconnected from each other. It deals with the nonlinear nature of science work. It deals with the fact that we're constantly doing rework. It's never a linear process. We're allowed to collaborate very easily with other data scientists because nobody works alone anymore. We want to pipeline our activities so that we get this reproducibility, but it also speeds up our work a fair bit. And this will all be addressed by, automating stuff, but this requires a learning curve that data scientists will have to go through. So and it's incomplete. It's, as you can see, it's glued together of a bunch of sort of standard tools, and then we're still missing a bunch of tools. And Literate Statistical Programming, if you follow this practice, you'll start building out tooling that you'll get this streamlined process. Thank you very much. And do you have any questions?
Thank you, John, for the great talk. We have a couple of questions. We ask that it is about your first part of your presentation. He asked, could you elaborate on institutional memory style?
So, sure. So institutional memory style is documentation that defines things that are typically sitting in an analyst's head. So an analyst would understand like, hey, there's a relationship between these three things. That's not necessarily documented anywhere. It's when they leave, that knowledge goes away. So the institutional memory is to document that so that the next person that comes and replaces them or their colleague that they work with has access to that knowledge. There should be no knowledge sitting in somebody's head that's not documented somewheres. What ends up happening is we end up having data scientists repeat the same process over and over again, make the same mistakes over and over again because they didn't learn from previous people's mistakes.
Yeah, you're right. And another question is that is there an automated method or option to tangle code with RMD?
Yeah, so with the R Markdown, it's built in as part of it. So you write an R Markdown document, and again, that can be Python or any other language, but it's called R. And when you just knit it, it does the tangle and weaving for you. So it will execute all the code and then output the document for you. It's done.
Thank you. Thank you so much for your great talk. And if you have any other thing to add, please do.
I think that's it. I'll stick around if other people have questions.
Thank you. Thank you so much. And thank you all for listening to this great talk.
Thank you for coming. So the question is, what do you recommend we work with when the models have different input formats? That's a very standard problem, and try to avoid proprietary data formats. It used to be that drive space was very expensive and people use proprietary formats for compression. Go with CSV as much as you possibly can. And the input that you're going to have is going to be independent from the analysis. So you're going to have operations within your literate statistical program that just picks up that data and reads it in whatever format that it's in, and then you operate, usually within like rectangular data, so like data frames and stuff like that, on that, and your analysis becomes separate from it. So the question is, what would be interested in understanding how unit tests integrate with LP and LSP? So I actually have another talk that I give on data unit testing. I actually built out a prototype at this at Amazon, and it operates the same way that quality engineers do unit testing now. So the difference would be is on the focus of what you're testing. So in unit testing, if you don't know, you would write a function. So I showed a function there, mean. So what you would do is you would pass in all kinds of different things. That function assumed that what you were getting was a single array. So you would write tests to make sure that it's a single array. It would assume that that single array was numbers and not necessarily text. So you would write tests where you would pass in an array of strings, and does the function handle that properly? So you're making all these assumptions when you write a function. You're going to do the same thing with your data. When you're doing your modeling, you're making assumptions around the nature of the data. These things are related, these things are highly correlated, these things are not correlated. So you're going to write tests that test the statistical assumptions that you're making with the data. So you're assuming that, let's say, that these two variables are not highly correlated. So you would write a unit test that says that they're not highly correlated, because if they're highly correlated and you're running linear regression, then it tends to cause problems with the linear regression. If you're doing a tree-based model where that's not a problem, then you don't write that unit test.
Okay, and if you have time, we have another question. Great. When referencing a database, Our markdown reference the parameters of the query, and params of the should be download the file locally and reference directly?
So the answer is both. So if it's a small amount of data, it's good to capture the data, and when you're building out your models, especially the first time, to be working off of a stationary set of data. So the data is not changing with time. If it's a large set of data, that doesn't make sense. You're not going to pull across, 20 gigabytes of data and store it in your project. So what you would store then is the query that you would use to access the database. You would do it in both cases. You always store the query. But if it's a small amount of data, store the data itself. And one that can act as a caching layer, but two, it also acts as a stable background. And it speeds up your process.
Thank you. Let me check if we have another question. It seems for now we don't have any other questions. Thank you so much again for your talk and for putting the time to answer all the questions.
No problem. Thank you guys very much for coming to the talk.